Now this is a continuation of our discussion on CUDA programming. Here we discuss the addition of two arrays. Now this is a C++ code that adds two large arrays. Okay. Now let's copy this code and compile it. Suppose we call the file to be addArray.cpp, and we paste this. Okay, so this is our file. Okay, so it is very straightforward. So we define a large constant n and a small value to check the error. Okay, so we use this function add to add two arrays a, b, okay, with n values. Okay, so we just use the for loop to do that, and the result is sum. Okay, is put in sum. Okay, so in the main we declared 3 pointers, and then we have to allocate the memory for the arrays. Okay, we divide the number of bytes, n bytes, to be the size of float, which is usually 4 times n. Okay, so a will point to this array. We use malloc to allocate n bytes to the array. Okay, we do the same for b and sum. Okay, and just for demo, we initialize the arrays. Okay, just set a elements to be 1, b elements to be 2, and then use the function to call it. Okay, and then do a simple verification to make sure that the difference of sum and ai and bi is smaller than the maximum error. Okay, and then more checking, we checked sum 0 to make sure it is 1 plus 2, that's 3. Okay, and print out the message passed. Okay, now let's compile this and run it. Okay, so we compile this using C++. Okay, so we compile it and run it. Okay, so we get the correct result. Okay, so this is the C++ program. Okay, yeah, if we want to change this to CUDA, okay, CUDA program, so we need to add this keyword. Okay, __ global to the program. So let's copy this, add array.cpp to add arrays.cu, okay, and make the modifications. So we just need to add this keyword. Okay, and also here we need to add these arguments. Okay, 1 1 and goes by angular brackets. 1 1 here basically means 1 block, 1 thread. Okay, so we add this. To here. Okay, and we save it again. Okay, and now, so this becomes a CUDA program, and we can compile it as we discussed last time using this command. Okay, and suppose we call our output to be arrays 1. Okay, as you can see, it compiles. Okay, but when we execute this, okay, the CUDA program, you can see that there's error. Okay, and a column. Now this is because as we discussed last time, okay, we have carried out the function, okay, the function here, okay, in the GPU memory, the execution, okay. But here we allocate the memory in the main memory, okay. So that's why we get a quantum, okay. So what we need to do is that we need to allocate the memory in the GPU, or also called device, okay, memory, okay. Allocate memory here, okay. And then when we get the result, we copy it result back to main memory, okay. And so CUDA provides these commands or these functions, okay, to do the memory allocation, very similar to the C syntax, okay. So it is called CUDA malloc, okay. The first parameter is a pointer to it is an address to the pointer pointing to the array that we want to allocate, okay. And the second parameter is the number base that we want to allocate, okay. And then cudaFree is to free the corresponding array or memory that we have allocated, okay. So for example, this code shows how to allocate the GPU memory. So we declare the n base to be the size of float, which is usually 4, okay, times n, okay. And then declare this pointer variable dA, okay, and CUDA malloc, okay, we cast it, okay, the address of this pointer, okay, and the n base, okay. This will do the job, do the work. This will allocate memory in the GPU memory, okay. And after we have allocated the memory, we need to transfer the data from the main memory, okay, to the GPU memory, because this is carried out in the main memory, okay. We need to do the transfer, okay. And the transfer can be done using this command CUDA memcpy, okay. So there's the destination, the source, the number of bytes to transfer, and then this is the keyword to tell us the direction, okay. Here CUDA memcpy host to device means to copy from the CPU memory to the GPU memory, okay. And so when we do the add the kernel function, so we use the GPU memory to do it. So dsum, DADB, these are allocated in the GPU, okay. And after we have done this, okay, we could transfer this back to the main memory, again using the CUDA memcpy, okay, from dsum to sum, okay. And the keyword here becomes device to host, okay, instead of host to device, okay. Now let's make these modifications, okay. So let's first copy this to, oh well, we don't need to copy it, we did the copy already. We just need to make the modification, okay. So there's no change here, okay. We just need to change here, okay. So we copy this, we copy all this, okay. We copy this, paste it here. Okay. Actually, we have defined n bytes here already, so we don't need this statement. Okay. And we need to do the same for b and sum. So we declare three variables, db and dsum. Okay. And here we do the same. So db and dsum. Okay. And the device. Okay. And then transfer the data from main memory to GPU memory. Do the same for the B. So dB B. Okay, so now we use DADB and dsum, okay, to work in the kernel. Okay, and after that we copy the sum back to the main memory sum. Okay, and do the verification, and then we can free it using the command cudaFree. Okay. UDA free. We do the same thing for B and sum. Okay. Now let's compile this again. Okay, so it compiles and now execute it. Okay. So you can see that now it works. Okay, after we did the allocation in the GPU memory. Okay. Now suppose we want to compare the running time for the two programs. Now this is by the C program. Okay. Okay. So you can see that okay, the time is pretty fast. Okay, 0.2 second. Okay, and the time for the CUDA program. Okay. And this is significantly longer. Okay. Now this is because we did the work in the GPU. Okay, we use one of the ALU, arithmetic logic unit, okay, in the GPU to do the work. Okay, and the ALU there works significantly slower than the main memory. Okay, I mean the CPU ALU, but the GPU has thousands of ALUs. So if we use many of these ALUs to work together, then we can speed up the process. Okay. And actually, NVIDIA provides a utility called NVPro for you to profiling the performance of a program. So what you need to do is to say NVPro, okay, 1, okay, then it will tell you say the time of transferring data, okay, and using the ALU to do the calculation, okay. So add, okay, so this is the main time free, okay, and then transferring data, it takes up a certain time, but in milliseconds, okay. So this is the time consuming part, okay. This part, okay. So in this program, okay, we have only used one thread, one block, basically one ALU. Okay. And as I just mentioned, there are thousands of ALUs in a GPU device. Okay. So if we use many threads to do it, okay, then we'll speed up the operation significantly. Okay. So we can do parallel operations by using multiple threads to do the operation. Okay. And in CUDA, threads are grouped into thread blocks. Okay. And thread blocks are grouped into grids. Okay. And now let's start with a simple example. We use one thread block, okay, and that thread block consists of 256 threads. So the syntax will be this, okay. This one means one thread block, okay, and the thread block consists of 256 threads, okay. All these threads would work in parallel, okay, and then yeah, we still have the same arguments, okay. CUDA also provides built-in variables for accessing thread information. So the thread IDX basically means index, okay. The X tells us index of the thread within the block, okay, or you can say that the ID of the thread ID, okay. And the block dim.x basically means the block dimension, okay. It tells us the number of threads in the thread block, okay. So in this example, suppose we use one thread block, okay, and 256 threads in the block, okay. Then it could be represented by a diagram like this, okay. So so in one block we have 256 threads, okay. So thread 0 would operate on the 0th element. So it do the add with A, okay, to B, okay, A0 to B0, okay. And then thread 1 will do this operation, okay, 1 to 1. And then thread 2 will do the operation on element 3 of A, okay, to element 2 of B, and so on. Okay, so this is a series of operation. And then after that, okay, thread 0 would jump to this location. Actually, in the array, this would be 256. Okay, thread 0 operate on this, okay, to this element in B, okay, and so on. So this is the first iteration. And second iteration. To trade, we have that many iterations. Okay. And in this example, the block dimension, okay, is 256. Okay. And so this is the code that we can use to implement this. So for simplicity, we define this variable TID basically means thread ID to be thread index dot x, okay? And we define the stride to be block dim dot x, the dimension of the block. So basically a thread has to jump over 256 locations after I finish this one. Okay, so thread 0 goes to here, okay, 256. Thread 1 goes to here, okay, also jumps over 256. So that's the meaning of the stride here. Okay, so the code will be, okay, we start with the I to be TID, the thread ID, so I equals 0, okay, for example, for thread 0, okay, and for the first iteration, and then after that it jumps over, okay, to this one, so increment it by stride. Okay, for the same for thread 1. Thread 1 is start with location 1, then it jumps over to here. Okay, so that's what this means, and that's the sum. Okay, so this is the code using one block 256 threads. Okay, now let's do this modification. Okay, maybe here. So we copy this arrays.cu to arrays T means thread here, cu. Okay, and then we added this. Okay, so we add this. Just for simplicity, we just copy this. Okay. So we copy this. And we don't need this anymore. And then here we just need to change this to 1 and 256. Now you begin to understand what these values mean. Okay, 256. So one block, 256 threads. Okay, and we compile it here. Oh, maybe I cut it. Okay, this one. And so this will be T. We compile this. Okay, so it compiles again. Now we can run this. So again, it passed. Okay, now let's check this profile. Now before it took 3 seconds, okay, to do the work, and now with 250 threads, let's see how long does it take. Okay, now it is T here. Okay. So you can see that now the function only takes about 23 milliseconds, okay, instead of 3 seconds. Okay, so that means there's a speed up of more than 100 times. Okay, and this, okay, data transfer are still the same. Okay, data transfer. Okay. But overall, we have a speed up factor of over 100. Okay, so this is the situation using one thread. One block and 256 threads. Now we can even do better by using more than one block. Okay. So in this case, we say that we are using the grid. Okay. and the griddim variable here, griddim.x, okay, will tell us the number of blocks in the grid. Okay, and so now we suppose we use multiple thread blocks instead of one, like this case. Okay, we just use one block. Now we use multiple blocks. Okay. The multiple blocks, okay, could be calculated using this formula. Okay, suppose each block contains 256 threads. Okay, then total number of thread blocks that we could use, okay, it can be given by this formula, the ceiling function of n divided by 256. Okay, or if you translate that to the code, okay, you can use a piece of code like this. The block size to be 256. Okay, that means each block has 256 threads, and the number of blocks, okay, would be n plus block size minus 1 over block size. Okay, basically it means the ceiling function of n over 256. Okay, and the arguments here becomes n blocks, and then the block size, okay, number of threads in a block, and the number of blocks that we are using. Okay, and this diagram shows an example, okay, the operation on the array. Okay, so here we have say the block index.x to be 0, or block 0. Okay, and this is block 1, block 2, so on. So this, if the dimension is 4096, this will be block 4095, 0 to 495. Okay, and within this block, we have 256 threads, the same for the next block. Okay, and all these threads and blocks will work in parallel. That means they work simultaneously. Okay, they carry out the addition simultaneously. Okay, and now, so we provide one long array. Then we need to know which thread is working on which element. Okay, now this can be easily calculated using this formula. Now suppose we are adding this element, okay, highlighted here, the third element of block 2, okay, then the index, okay, of the array, okay, to this element will be given by, say, the offset within this block. Okay, there's a block index.x times the block dimension. Okay, so here's the 256 times that. Okay, so we get to this block. Okay, plus the thread index. Okay, like here it is 2. Okay, so in this example it will be say 2. Okay, times 256 plus 3. So this offset is 3. Okay, so it points to this element. So it is, the offset is 515. Okay, so that's how we calculate the position of an element in the array. Okay, using this formula. Okay, so that means say our code, okay, could be simplified to this. So we calculate the index, basically the thread ID. So each element is operated by one thread. Okay, so the I is block index.x, okay, times block dim.x plus thread idx.x. Okay, so this will be our piece of code. Okay, so that's what we need. Okay, this piece of code. Again, now let's make the modification. So suppose we call this should be add arrays G. G means criteria CU. Okay, and so we make the modification. Okay. So we paste this. And here we need to make this modification using this formula. We copy this. Okay, so we don't need this. We need this one. Okay. And now, suppose we compile this. So this is the G. So it compiles, and again you can execute. So no error. And now let's do the profile of this. Okay. Now, before this is 23 milliseconds. Now we use multiple blocks. Okay. This is G, and you can see that okay, the add function takes even less time than the data transfer. It becomes 3 milliseconds. Okay, well 3.7. Okay, as compared to this 23. Okay, so it's another speed up of almost 7 times. Okay. Okay, so from this example, now you can see how we can do CUDA programming in parallel. Okay, so you could try this yourself. Okay, and if you think that this is helpful to you, please give the video a like. Okay. Yeah, thank you for watching. Okay, bye.